हेलो दोस्तों।
Hello.
Yes, sir.
Have you got the textbooks and PDF,
Yes,
PPTs?
sir.
Yes, sir. Yes, sir.
Okay, fine. So, if I go to the discussion, today we'll have a small class, 45 minutes or half an hour. So, the class I will send one assignment. Before that, you should start to read the first two chapters of the textbook, Pikenag or maybe Senjel Bulls. And after that, if you see the examples and start to solve the numerical, then you will find that there will be a lot of doubts. So if you accumulate those doubts, we can discuss those doubts in the next class. Even if you have still some doubts, we can discuss those doubts at the end of the class. So before that, I'll just start recording. My slides are visible?
Yes, sir.
Okay, so what we are discussing in the previous class, that a system can interact with the surrounding, or more precisely, a closed system can interact with the surrounding by heat transfer and the work transfer. So definition of moving boundary work we have discussed, what is called quasi-static process and how to locate the path. Then we discuss what is the expression of work done, which is integration of PDV for moving boundary work. Then we discuss the sign of the work. The work done by the system is positive and work done on the system is negative. So then we discuss that work is basically a path function. So it is not like a property. So it will depend upon that which path you are following to reach the other state. Based on that, the work done will change. So now then we discussed for a polytropic process, what will be the expression of work done, how to find out for any polytropic process. Just like for what is the work done for isothermal process, we know that the work done is represented in a PV diagram by the area under the curve. Then these are the different types of polytropic process. Then we discussed about what is called heat transfer and the convention of the heat transfer. If heat is being added to the system, it is considered as a positive heat transfer. If heat is being rejected by the system, it is called the negative heat transfer. Then we discussed some important aspect of heat and work transfer, from where we concluded that a system cannot possess heat or a system cannot possess work. It can possess energy whenever it needs to transfer this energy or it needs to accept energy from surrounding, then only the heat and work comes. So heat and work are basically the kind of currencies. So there is nothing called total heat or total heat content of a body. These are exist at the boundary phenomena. Okay, so this is one important thing. And if I discuss the first law after describing the heat and work. If I try to summarize, so what is the statement of first law? It is said that the first law of thermodynamics is that if a control mass undergoes a cyclic process, the cyclic integral of heat is proportional to the cyclic integral of work. So according to what we have discussed till now, that cyclic integral of heat, if you consider a cyclic process, I already have discussed what is called cyclic process. Cyclic process is that you start from some point and passing through some intermediate points, and after that if you again come back to the initial state, this process is basically called a cyclic process. Cyclic process is 1 to 2 through B and 2 to A through A. So this whole process is basically called a cyclic process. So what the first law statement says that for a cyclic process, the cyclic integral of heat equal to cyclic integral of work. What is the physical meaning of that? If we try to see the diagram, suppose this is one gas chamber, and inside the gas chamber you have one paddle wheel. So if we apply some work, basically you are adding some potential energy. This potential energy is causing a rotation of the wheel, and which is driving this paddle wheel. So basically you are adding work to the system. So basically work done is on the system. This is basically a negative kind of work, so whatever it is. But whenever you are adding some gas, adding some work into the system temperature will go up. So what will happen if the system temperature increases? After that, if we allow for a heat transfer process, the heat transfer, it will reject some amount of heat. So what they are trying to say, if the initial state of the process, you started to add some amount of work, after that you goes for a heat rejection, and again coming back to the initial state, the work added to the system is proportional to the heat rejected, or the vice versa. So if we go back to the previous system, that for a cyclic process, the cyclic process, whenever you are moving from point 1 to 2 through the path B, there will be some heat and work transfer. So the area under the diagram is basically your work transfer, and during this process there will be also some heat transfer. And whenever you are coming from the point 2 to A, there will be some heat transfer and there will be some work transfer, whatever may be the sign. During this process, from 1 to 2, work done is negative. Maybe heat transfer is negative. Whenever you are coming from 2 to 1, the heat transfer may be positive, the work done may be positive. I don't know, I'm not bothered about the sign. But during this whole process, if you sum up what is the heat transfer and if you sum up what is the work transfer, they are equal. So net heat transfer for a cyclic process is equal to the net work transfer. That is basically the statement of the first law. So consider that what I'm trying to say, if I try to explain it through a diagram, consider this is a cyclic process. What process? This you are at the point A1 and this is the point 2. You are moving from the point 1 to 2 through a process which is connecting 1 and 2 through the path A. So whenever you are moving from point 1 to point 2 through the path A, there will be some heat transfer as well as there will be some work transfer. Okay. Now after reaching to point 2, you are again coming back to the point 1 through the path B. During that process, there will be also some heat and work transfer. So what first law says that the cyclic integral of dq equal to the cyclic integral of dw. What is the meaning of that? The summation of heat transfer through the path A and B, so which is represented in the next line, that 1 to 2 del QA. So 1 to 2 del QA means the heat transfer during the process 1 to 2 through the path A. We know that whenever you are talking about heat transfer or whenever you are talking about work transfer, you need to specify the path. Okay. Now, whenever you are coming from the point 2 to the point 1, there will be some kind of heat transfer that will be integration 2 to 1. 2 is the initial state, 1 is the final state. That is dqb. So this is the net heat transfer. Is it positive? Is it negative? I am not bothered about that. I am considering that all those cases my heat transfer is positive. If it is negative, the sign automatically will be taken care of. So you don't need to bother about that. So initially there will be heat transfer, and if you come back from 2 to 1, there will be some heat transfer. During the process 1 to 2, whenever you are traveling through the point A or the path A, there will be also some work transfer. And whenever you are coming from point 2 to 1 through the path B, there will be also some work transfer. So according to the first law, this summation of heat transfer is equal to the summation of work transfer. Do you got my point? So if we sum up for each path, what will be your heat transfer? If you sum up for all those cases, and also for this path, if we sum up these two, and that should be equal to the sum of work transfer. So summation of dq equal to summation of dw. So we know that integration is nothing but the summations. So these are basically the summations. Now this is valid. The dq equal to dw, this is valid whenever there is a cyclic integral. This law is valid for only cyclic process. For any process, heat transfer is not equal to work transfer. Only for a cyclic process, the net heat transfer equal to work transfer. Why there is a cyclic process, that I will tell you later. Just wait for a minute. But you consider that these two integration signs are different. One is a simple integration, one is a cyclic integration. So you need to take care about the cyclic integration. The cyclic integration is valid for only cyclic path. Okay, so next look into the path which is basically between B and C. So what is happening for B and C? This is also a cyclic process. So you are basically moving from point 1 to 2 through the path C, and from 2 to 1 through the path B. So it is basically this cycle. So you are traveling through C and coming back through B. If this is a cyclic process, we can also write this line, the bottom line, that integration 1 to 2 dqc. So when you are traveling through C, there will be some heat transfer. Whenever you are coming back through B, there will be some heat transfer. This summation of heat transfer will be equal to, when you are traveling from 1 to 2 through the path C, there will be some work transfer. Whenever you are traveling from 2 to 1, there will be some heat transfer. The total heat transfer equal to total work transfer. Any doubt up to this much? Should I repeat once again? So here I am considering two cycles. The first cycle has two paths, A and B, and for the second cycle you have two paths. One is B, another one is C. Any doubt? Is it okay?
Yes, sir.
Yes, sir.
Okay. So if you follow the next part, so if you have these two paths, you will see that what is the common in these two paths? Which path is common?
B.
B is common. So if we subtract these two equations,
B.
if this is my equation 1, if this is my equation 2, if I subtract these two equation 1 from 2, I will get something like this. If you follow here, do you see my mouse pointer? So
Yes, sir.
So if we follow my mouse pointer, you will see that it is 1 to 2 dqa minus 1 to 2 dqc. 1 to 2 dqa minus 1 to 2 del qc. So in this case, you are this del qb and del qb, these two terms getting subtracted. As they are getting subtracted, only dqa minus dqc is existing, because I am subtracting this equation from this equation. So I am getting this equation. So if we take this work wqa in the left side and 1 to 2 dqc in the right side, so I will get an expression which is written as 1 to 2 dq minus dwa, 1 to 2 dq minus del w path C. So basically what I am trying to say, if am at the point 1. From point 1, I am traveling to the point 2 through a path A. During this process, I have a quantity. That quantity is dq minus dw. So dq minus dw is basically one quantity. So that quantity is changing. So this is the change of this quantity, and the right side term 1 to 2 dq minus dw. So you are traveling through the path C. So you are traveling to the path C through 1 to 2, and during this process there will be also a change of dq minus dw. But from mathematics you can see that this dq minus dw through the path A and dq minus dw through the path C are giving equal value, which was not happening for your work and heat. If you consider heat, if you are traveling from 1 to 2 through the path A, if you are traveling from 1 to 2 through the path C, in these both cases, your heat transfer is not equal. You know, because it is a path function. If you consider in terms of work, if you are traveling from 1 to 2 through the path A, and if you are traveling from 1 to 2 through the path C, in those two cases, you know that your work transfer is also different, because we know that the area under the diagram is basically your work transfer. But for a special parameter, what is that parameter? That parameter is dq minus dw. So dq minus dw through the path A is exactly equal to the dq minus dw for the path C. So this is very interesting. So this means that dq minus dw is basically what is this? dq minus dw is what?
State function.
Is a state function. Excellent, very good. So you understood my point. So what happens for the volume? So if you are traveling from one point to the other point, there will be a volume change. If you are traveling from one point to the other point, there will be a volume change. But whatever volume change happens for the path 1 and whatever volume change happen for the path 2, they are same. That means that volume is my property or maybe a state function. Similarly, you understood that this dq minus dw through the path A and dq minus dw through the path B, they are giving equal value. Something like what happens for your volume. So this means that dq minus dw is basically a property. Then only it can give equal values. So this is basically called, this term dq minus dw is basically a state function or maybe a property, and it is termed as what? Internal energy. So if you see follow the last line, I don't know it is visible or not, that dq minus dw you are writing as dE. So what is the meaning of that? The left part is basically a exact differential and the right part is basically a inexact differential. But these two differences of these two inexact differential is giving you a exact differential. Mathematically is also very interesting that one is imperfect differential or inexact differential, another one is also inexact differential, but whenever you are subtracting these two, it will become an exact differential. So basically you have two path function. If we subtract those two path function, it will give you a point function. It doesn't happen for always cases, but this case it is giving. So this difference is basically called the internal energy. Okay. So what is the meaning of that? If we follow the last line, so if we follow the last line, if I keep dq in the right side and take dw in the right side, left side, so this will become as dq minus dw equal to dE. So finally I can integrate this. If I integrate dq minus dw, it will give me E2 minus E1. But integration of dq will not give me q2 minus q1. Integration of dw will never give me w2 minus w1. But the dq minus dw, it will give me E2 minus E1. So because it is an exact differential. So I can write that q1 to 2 minus q1 W122 will give me E2 minus E1. So what is the physical significance of this? Physical significance is that if you change the side, that you can write that Q12 equal to delta E plus W12. I am repeating, you can write that Q12 is equal to delta E plus W12. This is also a form of first law. This is also a form of first law. You got my point? Now I have one question, like one tricky question, that whenever I'm starting this derivation, I told you that cyclic integral of heat equal to cyclic integral of work, or summation of heat equal to summation of work. Now I am saying that heat equal to change of internal energy plus work. Is these two statements are contradicting?
No, sir.
এইটা তো স্যার মানে এখানে যে সাইক্লিকই নয়, এখানে তো মানে হচ্ছে 1 2 মানে হচ্ছে ওই 2 পর্যন্ত, তো ওটা তো আবার যে রিভার্সে ফিরে আসছি না আমরা,
Very
ওই
good.
2
So,
to 1 তো আসছে না, এটা তো জাস্ট একটা পাথেরই,
excellent. So
মানে যে একবারই আর কি।
perfect. So what I was trying to say, summation of heat equal to summation of work, it is valid for a cyclic process or maybe for a loop. But for a single process, for any process, it does not need to be again come back to its initial state. For any process 1 to 2, you can say if I supply some heat, there will be some work done and there will be some kind of internal energy change, and which is very obvious. So if you have a gas cylinder, if you have a piston cylinder, and in between there is some amount of gas, if we supply some heat, what is going to happen? The gas will heat up. So whenever the gas will heat up, what is the meaning of this? The internal energy increases. That is basically the delta E. And the gas will, whenever you are adding some heat, the temperature will change. Along with that, the gas may expand. So if the gas is expanding, what is going to happen? There will be some work done. So it is very simple that if you take any system, you supply some heat, there must be a change of internal energy and there will be some work done. And the amount of heat you have supplied, that is equal to the internal energy change plus the work done. So if I try to say in a form of statement, the change in energy of a system during a change of state is numerically equal to the algebraic sum of heat transfer during the process and the work transfer during the process. So you forget the complex statement. In a what I can say that if we supply some heat, this heat transfer is equal to the work transfer plus internal energy. So if you are supplying 100 unit of heat, if you are supplying 100 unit of heat to a system, there may be 85 unit that is expended for increasing the internal energy, and the remaining 15 will be work done. But the left hand side is equal to right hand side. The 100 equal to 100. That is my point. So this is the thermodynamic definition of first law. But you already have studied something that energy cannot be created, energy cannot be destroyed, it can be converted from one form to the other form. So this is basically this is also the statement of first law. But if we derive the statement, if you try to extend the system for a closed system, closed thermodynamic system, you can interpret it in the form of this. So as you are becoming the engineer, so now whenever someone asks you that what is the statement of first law, you will say that for a cyclic process, the net heat transfer is equal to the net work transfer. You are not going to say the previous statement that energy cannot be created. This one is more kind of a gross kind of statement, but that is more generic. That statement you can apply anywhere. But whenever you are trying to say the first law of thermodynamics, then you are going to say in this statement, in this simple compressible context, like for a piston cylinder system, this will be your statement that the net heat transfer is equal to net work transfer for a cyclic process. Or maybe for a simple process, for any process, if I supply some heat, it will cause some change of internal energy and there will be some work done. The net heat transfer is equal to the change of internal energy plus the work transfer. So the most important one, the most important word for defining, first law is basically the word cyclic. If you are not using the word cyclic, it will be something different. If you are mentioning the word cyclic, then it will be different. But we understood that how these two are related. So this statement is evolving. This statement is basically giving me a new property. This new property is called the internal energy. Okay. So what I can say that whenever you have property, you need some kind of reference value. So I will discuss about the reference value later. So whenever you are supplying some amount of heat and or maybe work, and the system is leaving some amount of heat or maybe some amount of work, that will finally cause a change of internal energy. And now the question is that what do you mean by internal energy? It is very interesting thing that what do you mean by internal energy? This internal energy is basically some kind of microscopic energy. It is basically deals with, for a compressible system, simple compressible system, for a piston cylinder system, it is defined as basically the molecular kinetic energies. Okay, so whenever you add some heat, this will cause the increment of the internal energy or the molecular kinetic energy of the particles. This is basically called the internal energy. So if I try to solve one problem, do you have pen and paper in front of you? So if you have pen and paper, you can note down the question that a stationary mass of gas is compressed without friction from an initial state of 0.3 meter cube and 0.105 megapascal to the final state of 0.15 meter cube and 0.105 megapascal. The pressure remaining constant during this process. There is a heat transfer of 37.6 kilojoule of heat from the gas during the process. How much does the internal energy of the gas changes? So basically what is happening, if I make it simple, that you have one gas, the initial state is mentioned, this is the initial state, and there is the final state. So you know the final state. So initial state, they have mentioned the temperature, they have mentioned the volume and the pressure, and the final state, they have mentioned the volume and the pressure. So you know the initial and the final state. And during this process, they also mention that what is the amount of, during the process, how much internal energy is going to change. So basically it is talking about that you know heat transfer, you know initial and final state. So what will be your change of internal energy? So as they have mentioned the initial state, the pressure and the volume, and final state, the pressure and the volume. If I carefully look the initial state, I will see the pressure is same. So whenever the pressure is same, so it is basically kind of a what? Is a kind of a isobaric process. Is that right? Fine. So for isobaric process, what will happen? The pressure will remain constant. So work done, the expression of work done is known to me because we know that integration P dV. So P is constant. So I can take out the P. So V2 minus V1 is my work done. So now another interesting thing is that you know that the initial volume is high and the final volume is low. So it is basically compression work. but you don't need to bother about that. Whenever you are performing the integration, if you see the thought, you don't need to bother about that. It is the expansion or compression. The integration simply PDV, initial to final, will take care of it. Now you know work done, and you also know heat transfer. So you have one summation rule that heat transfer equal to change of internal energy equal to work transfer. So heat transfer, what they have mentioned, that there is a transfer of heat. Please read the sentence carefully. There is a transfer of heat. There is a transfer of 37.6 kilojoule of heat from the gas. The important word is from. From means, what is the meaning of from? From the gas. The gas is losing heat. Correct. So, when the gas is losing heat, what is the meaning of that?
Negative.
So, it is a negative.
Q negative.
Q is negative. So, if I take this, if you consider the first line and this substituting the equation 1. So, if you see this line, this Q is going to become negative. The work done, which is already came negative, I will put the direct sign there, negative. And finally, I can find out that E2 minus E1 equal to, it will also come negative, minus 21.85. What is the meaning of negative delta U? The meaning is that the internal energy decreases.
Decreasing.
Very good. So this is the conclusion. So two things is important here. One part is that how to calculate work, how to take care of the sign, and how to apply the first law of thermodynamics for a process. This is the whole conclusion of this problem. So in this section, we are going to solve different kinds of problems. So what will be the next kind of problem? In this case, the work done will not be so simple. So simple. In that case, maybe there will be a polytropic process. So you need to do some mathematical steps to find out the work done. For heat transfer, the heat transfer will not be so simple. For heat transfer, you have to do some mathematics. So, but the main funda is same. You have one heat transfer, one first law for a process, and based on that, you will calculate what is going to happen. So this is basically the problems of this chapter. So I will send you some problem. Before that, I am giving you 1 minute. You just take out one A4 sheet or maybe a piece of paper and a pen, and please just like sit and try to solve one numerical. I am showing in the next slide. So if you have one pen and paper, if you solve this problem, then the main idea behind the first law of thermodynamics will completely get cleared. So please solve this problem. I'm waiting that what answer you are going to get. Do you have pen and paper? Please bring a piece of pen and paper. So if we read the question, when a system is taken from the state A to B, so A is the left bottommost point, and the other point is B, the right topmost point. Along the path ACB, so A then moves vertical C, then moves right to B. What is happening that 84 kilojoule of heat flows into the system. Very good. So heat flows into the system means positive heat, and the system does 32 kilojoule of work. So the system done means the work done by the system, so it is positive. Now what is the first question? That how much heat will flow into the system along the path A, D, B. What is the ADB path? ADB path is the bottom triangle. So you are traveling from A to B, A to D, then D to B. So you are moving in the rightward direction, then you are moving in the upward direction. So they are saying that what will be the work done during the process ADB if work done is 10.5 kilojoule. Okay. Can we solve this question?
62.5.
62.5.
62.5.
How you are doing that problem?
So
Sir,
the DU is constant and
we need to turn
DU constant and DW as 10.5. We can find the DQ.
So basically you are trying to say that delta U is constant.
Yes, sir.
Delta U, why delta U is constant? Because it is internal energy, it is a property.
Yes, sir.
It is not a path function, so
Very good.
it will remain constant.
So it is very simple. So the next question, let's see the B. So when the system is returned from the point B to A along the curved path, so it first reaches to A, C, B, then it is coming back to B to A. The work done on the system is 21 kilojoule. Very good. Now work done on the system means it's a negative work. Now, does the system absorb or liberate heat? And how much of the heat is absorbed or liberated? The same kind of problem. So you know the change of internal energy. So if you know the change of internal energy, so again if we apply the first law, you can find out that what is the value of heat to absorb. So what is the value? B.
31. 31.
Careful about the sign. Sign is okay?
Positive.
Yes.
Positive sign.
So basically you are supplying heat.
Yes, sir.
Okay, so now
No, sir. Q is actually minus 73 kilojoule.
maybe
Minus 73, sir.
Rejected. Heat will reject. Heat will be rejected.
so your Q
B2A. The path is B2A, so it will be negative. Sorry.
Yes.
so exactly. So that's why I was talking to very careful about the sign. So you need to simple problem, simple summation subtraction. But if you make a small mistake, then it will be completely wrong. So the understanding of sign is very important. That's why in the first time I told that be careful about the sign, because whenever you are doing some work on the system, the work done become negative, and you know the delta Q, and you are coming from B to A. So it is basically reversing. In the previously, you know U2 minus U1. Here it will be UA minus UB. Okay. So very good. So now look at the last question. If U subscript A, that the internal energy at A equal to 0, very good, and the internal energy at D equal to 42. Find the heat absorbed during the process AD and DB. So A internal energy known to you, D internal energy given to you. Already you know what is your delta U. From that you can find out what is your UB. Now they have asked that find the heat absorbed in the process A to D and D to B. Heat transfer during the process A to D, what is the answer?
52.5 kilojoule.
52.5.
Anyone? Any other answer?
52.5, sir.
For D to B?
And the
10
next one is
kilojoule. 10 kilojoule.
work done.
D to B?
10 kilojoule.
10
D-
kilojoule. So if now what you can do, just for your verification, you consider the loop ADB. Just consider the loop ADB. This cyclic process, just check that the summation of heat is equal to coming the summation of work. If you have done the second part, D to B, after that, just verify that A to B, A to D, D to B, B to A. For all these three processes, you know the work transfer and the heat transfer for every cases. Is it coming? So what is the heat transfer for A to D? You told it 52.5.
Yes, sir.
And what is the work transfer? Work transfer was given
Work transfer,
10.5.
it will be the 10.5.
Work transfer is 10.5.
Yes, sir.
Huh? No, it is not 10.5. Yeah, it is 10.5. Because
Yes, sir.
D to B is
D
a
is
constant,
0.
is constant volume process, it is 0. So you know the work transfer here. Now for B to D, from D to B, you know what is your heat transfer? 10. Now from B to A, you already calculated what is your heat transfer. And you know that the 21 is basically the work transfer. Are they coming to 0? Left hand side equal to right hand side? Heat transfer equal to work transfer. Is it coming? If it is not coming, you are doing mistake. কেউ ভেরিফাই করলে? কেউ ভেরিফাই করলে? Am I audible still?
Yes, sir. It is coming.
In the process. So take your
Yes.
time.
Sir,
Yeah. Are you getting that?
so no, there's a question that in the first part,
Is it coming full?
So no, I have another question, different question.
Yeah.
So in the first part, we saw that the internal energy, the change in internal energy from A to B is 52 kilojoule
A to B is 52 kilojoule. Yeah.
in the first part, and in the last part it is mentioned that the initial the internal energy at A is 0.
Yeah.
So can we say that the internal energy at B is 52 kilojoule?
Yes, exactly.
So then the work done at from D to B. Okay,
Yeah.
okay,
It is coming 10.
we can find that yes, 10 only.
So the complete heat transfer is expended for increasing the internal energy because there is no work done. Is that right? So as
Yes,
there
sir.
is no work done, whatever heat transfer you have done, the complete heat is converted into internal energy. There is no part of work done. Any other question? If you keep your notebook handy during the class, it will be easier for you to follow this. I know that maybe the 50% student do not have notebook in front of them, but from next class, if you keep it so we can learn together, so it will be easier for us. Anyway, but still what you can do, I will send you, already have forwarded some textbook, you start to read and see some examples, and within couple of days I will send you the problem sheet. So whenever you are going to solve the problem sheet, that time you need to consult the textbook and see some examples, and based on that, after that you solve those problems. And what you can do for formalities, you can send me the soft copies of your solved assignment, but I finally found that you will somehow you will collect those things and forward it, but you do it for yourself. If you have any questions and ambiguities, we can have some doubt clearing class. Okay, so if you have no further doubt, I can stop right now. Yeah, please ask.
So, is it possible that 100% heat is converted into 100% work?
Yeah, it is possible. It is possible. So what is the meaning of that? Basically, for any isothermal process, your temperature is constant. So we know that the internal energy is basically a function of temperature.
Yes.
So if you, for an isothermal process, whatever heat you are going to supply, that complete heat is going to convert into work. Similarly, for the previous example, for a isochoric process, constant volume process, what is going to happen? That the complete heat is going to convert into internal energy.
Yeah.
Do you get my point?
Yes, sir. So, can you give a practical example where it is 100%? Like in machines, there is always not 100% heat is converted into work.
Okay. I got your point. I will come to this part whenever I will discuss the second law. So whenever you are talking about a machine, this machine is basically kind of a, most of the cases, the machine is basically runs on a cyclic process. It is not like a single process. So it operates on a cycle. So that part I will discuss in the second law, that we know that